Hello everyone, welcome to IIT and Gate classes. Today we'll see the solution of gas dynamics and propulsion questions of GATE 2009 paper. In GATE 2009, around 14 questions were there from gas dynamics and propulsion, out of which 8 were of 1 marks question and rest are all 2 marks question. We'll see the solution of all these questions today. First question. For a flow through a Prandtl-Meyer expansion wave, which of the following options are correct? That is, Mach number stays constant, entropy stays constant, temperature stays constant, density stays constant. So a Prandtl-Meyer expansion wave occur when a supersonic flow turns away from itself. So which is like this. So suppose there is a corner like this, and a supersonic flow encounters a corner like this, then at the corner the expansion wave form. So these are the expansion waves. So this is forward Mach wave, this is rearward Mach wave. So expansion wave is basically a group of Mach waves which is forming in the corner when the supersonic flow is turning away from itself, right? Now this expansion wave, the flow across this expansion wave is completely isentropic process. The flow across the expansion wave is an isentropic process. So as the process is isentropic, so there is no loss. So obviously the entropy is constant. Suppose this is upstream condition, which is denoted as 1, and this is downstream condition of the expansion wave, which is denoted as 2. And if the properties are as follows: T1, T1, rho 1, and these are T2, T2, rho 2, M2, right? So as the process is isentropic, so the entropy remains constant across the expansion wave. And so entropy remains constant, first point. And as this is isentropic and hence no loss is taking place when the flow is occurring across the expansion waves, so total pressure and total temperature also remains constant, right? So total P naught denotes the total pressure, T naught denotes the total temperature, both remains constant. So because there is no heat addition or heat subtraction from this flow, so T naught will remain constant. And as this is isentropic, which is reversible, so the total and hence no pressure, no loss is taking place, since total pressure will also remain constant. Okay, and then what about the static properties? Static for flow across expansion wave, the Mach number always increases, that is M2 will be greater than M1, and P2, that is static pressure downstream of the flow, will always be less than P1, and static temperature will also be, static temperature downstream of the flow will also be less than the static temperature upstream of the flow. So this is T1. And also the static density downstream of the flow is less than static density upstream of the flow, right? So for this particular question, the correct answer is entropy stays constant, because density, temperature, Mach number, so this temperature is basically the static temperature. So static temperature, Mach number, density, none of them remains constant across expansion wave. Next question. The propulsive efficiency of a turbojet engine moving at velocity u infinity and having exhaust velocity ue with respect to the engine is given by, okay, which of the following is correct? So the propulsive efficiency of a turbojet engine is propulsive efficiency of a turbojet engine is defined as a ratio of thrust power of the engine and propulsive power of the engine, right? So thrust power divided by propulsive power. Now thrust power of the engine is defined as thrust produced by the engine, which is thrust produced by the engine So this is thrust produced by the engine, which is ma dot multiplied by ue, which is exhaust velocity minus u infinity, which is the velocity at which the aircraft is moving. So this is the thrust power produced by the engine, and the propulsive power of the engine is defined as the change of kinetic energy of the flow at the exit of the engine and at the compared with the entry of the engine. So this is defined as half ma dot into u square minus u infinity square. So half ma dot u infinity square, this is the kinetic energy of the flow at exit of the engine, and half ma dot u infinity square, this is kinetic energy of the flow at entry of the engine. So the differences of these two kinetic energy is defined as propulsive power. So if we substitute this expression here, we'll get eta p as divided by half dot. So this u infinity square minus u e square minus u infinity square can be written as u e minus u infinity multiplied by u e plus u infinity, right? So these two ma dot will get cancelled, and also u infinity minus this. So this will give 2 u infinity divided by ue plus u infinity. So this is the correct answer. Next question. An aircraft is flying at a Mach number 2, where the ambient temperature around the aircraft is 250 Kelvin. If the specific heat ratio for the air is 1.4, the stagnation temperature on the surface of the aircraft is. Okay. So the relation of the stagnation temperature with the static temperature is given as T naught divided by T infinity equal to 1 plus gamma minus 1 by 2 m infinity square or m square. Now where T naught is total temperature, T infinity is static temperature. Total temperature, and T infinity is static temperature. And m is of course Mach number. So and if we have to see how this relation is coming, then we have to go back to the definition of the stagnation temperature or total temperature. So stagnation temperature is basically defined as the temperature of a fluid element where the flow, so temperature of a fluid element at a particular point where the flow is brought to rest isentropically. Okay, So stagnation temperature is basically defined as the temperature of the fluid element at a particular point where the flow is brought to rest isentropically. Okay, so let's assume that one is a point. Let's assume one is a point where the temperature of the fluid is temperature of fluid element is T, and the element is moving at a velocity v. Now if this fluid element which is moving at a velocity is brought to rest isentropically, and that point is denoted as 2.2, then the temperature at point 2 is defined as stagnation temperature. Okay, so and point 2 is a point where the fluid element is brought to rest isentropically. Hence temperature at point 2 is T naught. Now if we apply the energy conservation rule, so total energy at point 2 is CPT naught, and total temperature at point 1 will be CPT plus, which is the internal energy of the element, and the kinetic energy of the fluid element, which is half v square, right? And as this is the fluid element has been brought to rest isentropically, so the total energy will remain constant. So this energy conservation rule will still hold true. So if we simplify this equation, if we take common Cp both the side, then it will be plus 1 by 2 Cp v square. And as we know that Cp is can be denoted as gamma R by gamma minus 1, where gamma is basically the ratio of specific heat Cp and Cv, and R is gas constant. So substituting that expression here, it will give gamma minus 1 by 2 gamma R into v square, right? So if we take T common, it will come as 1 plus gamma minus 1 by 2 v square by gamma RT. All right. Now this gamma RT is basically, so the speed of sound A is defined as under root of gamma RT. So gamma RT can be written as A square. So if we substitute this gamma RT with A square, the relation will become this, which is T naught. So okay, so if we just T naught will become T into 1 plus gamma minus 1 by 2 m square, right, which is this basically this expression. Now this is how this expression is obtained, but it is advisable that one should remember this expression, because this is very vital relation in gas dynamics and propulsion, and you should be able to directly employ this equation when this question is asked. So in this question, T ambient temperature, which is T infinity, is given as 250 Kelvin, and m is given as 2, and gamma is 1.4. So if we substitute all this, uh, if we substitute all this relation in this equation, it becomes into 2 square, which is 4. So if we solve this, it will come something around 450 Kelvin. Hence, option B is the correct answer. Next question. The division of feed air to an aircraft gas turbine combustor into primary and secondary streams serves which of the following purposes? A flammable mixture can be formed, cooling of linear combustor liner and flame tube can be accomplished, specific fuel consumption can be reduced. So the division of feed air into an aircraft gas turbine engine, that is primary and secondary streams, are basically done due to achieve the following reasons. Okay, which is the primary stream is injected for efficient ignition of the combustion chamber, and the secondary, the reason of injecting the secondary stream is basically to cool down the combustor inner flame tube, to reduce the turbine entry temperature, and also it reduces the release of nitrogen oxides. So these are main reasons of dividing the main air stream into primary and secondary stream. So the primary stream is injected to achieve an efficient combustion so to achieve an efficient ignition, flammability, which is the first option, and the secondary stream is for cooling of the combustor tube tube, and also it reduces the turbine entry temperature. And release of nitrogen oxides. So this is the second option, and it doesn't have any effect on specific fuel consumption. So this is not the correct correct statement. So only P and Q are the correct statement. So C is the correct answer. Next question. Thrust available from a turbojet engine increases as altitude increases up to tropopause and then decreases, remain constant at all altitudes, decreases as altitude increases. Okay. So the thrust available from a turbojet engine, that is T, is written as ma dot 1 plus F ue minus ui, where ma dot is the mass flow rate of the air into the engine, and okay, let me write all these details. So ma dot is nothing but mass flow rate of air into the mass flow rate of air entering the engine, and F is the ratio of fuel flow rate and the mass flow rate of air, that is mf dot by ma dot, where mf dot is the fuel flow rate which is being injected in the combustion chamber, and ue is nothing but exhaust velocity of engine, ui is velocity at which engine is moving, right? Now in this equation only ma dot is the quantity which depends on density. So this ma dot is can be defined as rho area and ui. Right. Now this a is the area of engine nacelle, which is engine the front part of the front area of the engine, and rho is the density of the air. So as this density decreases as altitude increases, so ma dot also decreases with altitude, and for that reason thrust also decreases with altitude. So as rho decreases with increasing altitude, ma dot also decreases, and as ma dot decreases, thrust produced by the engine also decreases. Hence, the decreases as altitude increases is the correct answer. Next question. Let m naught be the total mass of the single stage rocket, mp be the total mass of the propellant, ml be the mass of payload carried by the rocket, and ms be the mass of inert structural component. If isp is the specific impulse of the propulsion system in seconds, and g is the acceleration due to gravity, then the maximum velocity that can be attained by the rocket vehicle in the absence of gravity and atmospheric drag is given by which of the following is correct? Okay. So the velocity of a rocket is given by the following expression. Velocity of rocket v is ueln, the initial mass of the rocket and final mass of the rocket, right? Then this ue is exhaust velocity of the of the rocket engine of the nozzle. This UE is nozzle exhaust velocity, and the specific impulse is defined as ratio of UE and G, right? That is the nozzle exhaust velocity and gravitational constant. So in this equation, you can substitute UE as ISP into G multiplied by ln of the initial mass of the rocket divided by final mass of the rocket. So initial mass of the rocket is the total mass of rocket, which is given as m naught, and final mass of the rocket is, and this m naught is definitely the summation of the payload mass, the structural mass, and the propellant. And mf, that is the final mass of the rocket, is definitely the total mass of the rocket minus the propellant mass, because propellant is already burnt, right? So this is the final mass of the rocket. Now if you substitute it here, it will give g ln of m naught divided by m naught minus, hence this is the, and mp is the propellant mass as it is given here, total mass of the propellant. So this is the correct answer, option D. Next question. An ideal axial compressor is driven by an ideal turbine across which the total temperature ratio is 0.667. If the total temperature at turbine inlet is 1500 Kelvin and specific heat of gas is 1 kilojoule per kg per Kelvin, the power drawn by the compressor per unit mass flow rate of the air is approximately, which of the following is correct? Okay. So the for an ideal so when an ideal axial compressor is driven by ideal turbine, the power which is being drawn by the compressor is the power which is delivered by the turbine, right? So power drawn by compressor is equal to power delivered by turbine. So power drawn by the compressor per unit mass flow rate, that is what we have to find out. So this is the quantity we need to find out. And power delivered by the compressor, sorry, power delivered by the turbine, this can be written as ma dot, that is the mass flow rate through the turbine, multiplied by Cp into temperature, total temperature at the exit of turbine minus total temperature at the inlet of turbine, right? Now turbine inlet temperature is given as 1500 Kelvin, and the ratio of the exit total temperature and inlet total temperature is given as 0.667. So the power delivered, so here we have to find out the per unit mass flow rate, right? So this is going to be m dot multiplied by Cp, which is 1000 joule per kg Kelvin. So Cp is given as 1 kilojoule per kg Kelvin. So this will be nothing but 1000 joule per kg Kelvin, right? Into, sorry, here I have made a mistake here. So power delivered by turbine is m dot cp into T inlet, that is total temperature at the inlet of the turbine minus total temperature at the exit of the turbine. Now this T inlet, we know this is 1500 Kelvin, and T exit from this we can find out as 0.667 multiplied by 1500, right? So this is the power delivered by turbine and also the power drawn by compressor. And as we have to find out per unit mass, so power drawn by compressor per unit mass will be this quantity divided by m dot. So m dot will get cancelled and it will remain as 10 cube 1500 minus 1500 multiplied by 0.667. So this watt per kg second. So this will come something around 499500 watt per kg second, which is 500 kilowatt per kg second. This is the correct answer, right? Next question. A solid rocket motor has an end burning grain of cross-sectional area this, and the density of the propellant is this, and has linear regression rate of this. If the specific impulse of the propulsion system is 200 second, the thrust produced by the motor is approximately which of the following? Okay, so thrust produced by the rocket motor is given as m dot multiplied by UE, where m dot is the exhaust mass flow rate and UE is exhaust velocity of nozzle, right? Now this m dot, that is the mass flow, exhaust mass flow rate, is nothing but the mass which is being burnt per second from the propellant, right? So this can be written as the propellant density rho p, which is propellant density multiplied by volume of the propellant burnt every second. Right? So this rho p and volume is nothing but the cross-sectional area of the propellant uh, multiplied by the rate at which this is the propellant is being burnt. So rho p is given as 1500. The propellant density is given as 1500 kilojoule per kg per meter cube, and the cross-sectional area of the propellant is given as 0.4 meter square, and the rate at which the propellant is being burnt is given as 5 millimeter per second. So it will be in SI, it will be 5 into 10 to the power minus 3 meter per second, right? So this is kg per second. This is the mass flow rate which is being burnt every second, which is the mass which is being burnt every second. And UE, the specific impulse, can be given as UE divided by G. This specific impulse is given as 200, which is equal to UE divided by 9.806. So from here we can get UE as 200 multiplied by 9.806 meter per second. So if we substitute this and this in the equation of thrust, we will get T equal to 1500 multiplied by 0.4 multiplied by 5 into 10 to the power minus 3 multiplied by 200 multiplied by 9.806 this Newton. So if we calculate it, it will come at this Newton, which is approximately 6 kilonewton. Hence, this is the correct answer. Next question: an ideal ramjet is flying at an altitude 10 kilometer with a velocity 1 kilometer per second. The ambient pressure is 0.25 bar and the temperature is 225 Kelvin. The exhaust gases from the engine are optimally expanded and leave the nozzle at 900 Kelvin. If the specific heat ratio gamma remains constant, the specific thrust developed by the engine is approximately which of the following? Okay, so basically you have to find out the specific thrust of a ramjet engine, and the value of some quantity is given. Okay, so as per the given information, the ramjet is flying at a velocity of 1 kilometer per second. So UI, that is the velocity at which the engine is flying, is 1 kilometer per second, which is nothing but 1000 meter per second. Then ambient temperature is given as 225 Kelvin, and the nozzle exhaust temperature is given as 900 Kelvin. So for a ramjet engine, the thrust produced, so you have to find out specific thrust, but the thrust produced by a ramjet engine is T equal to ma dot multiplied by UE minus UI. So we are basically ignoring the fuel flow rate, right? So the expression will be this. So the specific thrust Okay, so the thrust produced by the ramjet engine is given as ma dot into 1 plus f ue minus ui, where ma dot is the mass flow rate entering into the engine, and f is the ratio of, so ma dot is mass flow rate entering into the engine, and f is the ratio of fuel flow rate to mass flow rate. UE is basically the exhaust velocity, UI is velocity at which engine is moving. Now this F is much less than 1. So we can 1 plus F can be written as 1. So this expression, so we can ignore basically 1 plus F term, as this is almost equal to 1. So this will come as UE minus UI, right? So the specific thrust is nothing but T by MA dot, which is UE minus UI, right? Now for ramjet, for an ideal ramjet engine, the Mach number of the exhaust gas is equal to the Mach number of the Mach number at which the engine is moving. That is ME will be equal to MI. So ME is the Mach number of the exhaust gas, and MI is the Mach number at which the engine is moving. So for ramjet, these are equal, ME equal to MI. So we can the ratio UI by UE, that can be written as MIAI into MEAE, as MI is basically ratio of AI and UI and AI, and ME is UE and AE. This A is the speed of sound, so AI is speed of sound at entry of the engine, and AE is the speed of sound at exit of the nozzle. All right. So this, and for for ideal ramjet, MI equal to ME. So UI by UE basically comes at UAI by AE. So this A is again can be written as gamma RT, where T is temperature, R is gas constant. So this will be AI will be equal to gamma RTI, and AE will be equal to gamma RTE. So gamma is gas constant, ratio of the specific heat, R is gas constant, and Ti is the temperature at the entry of the engine, Te is the temperature at the exit of the nozzle. So this gamma R both gets cancelled, so it basically remains as Ti by Te, right? Or Ti can also be written as the free stream temperature, which is Te T infinity by Te. Ti equal to T infinity. So the specific thrust T by M dot, which is UE minus UI. If we take common UI, it will become UE by UI minus 1. And UE by UI can be written from the above expression, that UI multiplied by TE by T infinity minus 1. Now we can substitute all this quantity, because these are given in the question. So UI is nothing but 1000, and TE was 900, T infinity was 225 minus 1. So this will come as 1000 Newton second per kg. So this is the correct answer. Next question. That is, a combat aircraft engine is equipped with afterburner followed by a variable area convergent nozzle operating with the nozzle choked. So the exhaust gas temperature is 750 Kelvin, and when the afterburner is off, and 3000 Kelvin when the afterburner is on. When afterburner is turned on, assuming the total pressure remains the same, the mass flow of fuel added in the afterburner is negligible. Um, then approximately by what factor must the nozzle area be increased or changed? Okay. So it is saying that the exhaust gas temperature without afterburner is 750 Kelvin without afterburner, and exhaust gas temperature is 3000 Kelvin with afterburner, right? And nozzle is choked. The nozzle is choked. So at exit of the conversion nozzle, exit of the conversion nozzle, Mach number is 1. Right. And the area of the exit of the nozzle is denoted as A star, right? And so mass flow rate through the variable area duct can be written as can be given by this expression, that is m dot, which is equal to p naught root over gamma a by root over r t naught multiplied by m by 1 plus gamma minus 1 by 2 m square to the power gamma plus 1 divided by 2 into gamma minus 1, right? So this is a very important expression of the mass flow rate through the variable area duct or through nozzle or diffuser. So once you remember this expression, it can be derived also, but the derivation is a bit long, so we are avoiding this from this solution. So you're directly employing this expression, and it is advisable that one should remember this expression because it is very important, and a lot of questions have been asked on this expression, right? So this is the expression of mass flow rate through the variable area duct, where p naught is nothing. P naught is basically the chamber pressure, a is the area of the nozzle, T naught is the chamber temperature, that is total temperature, M is Mach flow rate of the nozzle at a particular area, okay, where we are trying to find out the mass flow rate, and M is the again mass flow rate, sorry, M is Mach number, and gamma is ratio of specific heat. So now here in this case, as the nozzle is already choked, so at the exit of the nozzle, Mach number is 1 and A is noted as A star. So for the following, for the our problem, we can write A equal to A star and m equal to 1 at the exit of the nozzle. Right, so m dot by a star from the previous expression will come as p naught root over gamma root over r t naught 2 by gamma plus 1 gamma plus 1 by 2 gamma minus 1. So in the previous expression, in this expression, just we have substituted m equal to 1, and if we just simplify it, it will come something like this, right? Now in this expression, as p naught is constant for both the cases, for both with afterburner and without afterburner cases. Afterburner cases. So m dot by a star is basically inversely proportional to under root of T naught, that is chamber temperature or total temperature of the nozzle, right? And all other quantities are constant, that is gamma is constant, r is constant. So this is the expression we have got. Now in our case, it is given that mass flow rate is also, the mass flow rate remains same. Mass flow rate through the nozzle is remaining same. So in this case, m dot is also constant. So basically, so as m dot is constant, so what we are obtaining is a star, that is area of the nozzle, is directly proportional to under root of total temperature of the flow, right? So as here in this case, okay, so a star with afterburner divided by a star without afterburner is going to be T naught with afterburner and T naught without afterburner. So this is nothing but T naught is 3000 and this T naught is 700. Sorry, 750. So T without afterburner is 750. So this will come as 2. So you have to increase the area of the nozzle by a factor of 2. So by what factor must the nozzle area be changed? So you have to increase it by a factor of 2. Next question. Which of the following statements are true for flow across a stationary normal sock? Stagnation temperature stays constant, stagnation pressure decreases, entropy increases, stagnation pressure increases, stagnation temperature increases. Okay, so if we see the flow across a normal sock, so let's assume this is a normal sock and flow is there. So this is the upstream condition of the sock, and this is the downstream condition. So if we just take a control volume like this, and here m1 which is greater than 1, p1 t1 denotes the static pressure and static temperature respectively, and P naught and T naught 1 are the total temperature, total pressure and total temperature respectively. Now this flow across a normal sock is adiabatic process, right? So flow across a normal sock is adiabatic process. So no heat addition is there and no heat subtraction is there. So total temperature remains constant across the normal sock. Across a normal sock. So TO1 will be equal to TO2. So this option is not correct. This is correct. Now across a normal sock, entropy increases. So, and as entropy increases, total pressure decreases. So entropy increases. This is correct. Stagnation pressure or total pressure decreases. This is correct. And total pressure, stagnation pressure increases. This is not correct. So entropy, I mean the total temperature remains constant. Entropy increases. Total pressure decreases. And for the static quantity, the relations are as follows. So Mach number will always decrease. The pressure, static pressure will increase across a normal sock. Static temperature will also increase across a normal sock. So here the correct options are P, Q, and R, which is A. Correct. Next question. That is, a piston compress 1 kg of air inside a cylinder, as shown below in the picture, and the rate at which the piston does work on the air is 3000 Kelvin. At the same time, heat is being lost through the walls of the cylinder at a rate of heat 47.5 watt. After 10 seconds, the change in specific internal energy of the air is which of the following? So this is a linked question for, I mean, the statement are linked for both the questions. Another question is, given the specific heats of air at constant pressure and volume, this CP, CV are given, and corresponding change in temperature of the air, which of the following? Okay, so we know that the change of, from laws of thermodynamics, the change of kinetic energy is nothing but the work done on the system and heat added on the in the system, right? So this is nothing but energy conservation equation. So here delta W is work done on the system, and delta Q is heat added to the system, right? And du is change in internal energy of the system. Now here the piston does the work at 3000 Kelvin, so which means delta W is 3000 watt. So 3000, and the the work is being continuously done for 10 seconds. So total work done will be multiplied by 10, this joule. And heat uh, which is being lost through the wall of the cylinder is 847.5 watt. That is, as this heat is being lost, so this will be minus of 847.5. And again, this is being performed, this is being this is happening for 10 seconds. So total it lost is this joule, this much joule. So if we just substitute these two quantity here in the above equation, it will give us the specific internal the change in specific internal energy. So this will be nothing but du will be equal to into 10 minus 847.5 multiplied by 10. So this joule per kg. So this will come as joule per kg. So option A is the correct answer. And in the second part, second question, it is saying that specific heat of the air Cp is given and Cv is given, then the corresponding change in the temperature of the air. Okay, so we know that the change in internal energy can be written as Cv into dt, right? Can be written as Cv into dt. So du we have obtained here, and Cv is given as 717.5 joule per kg Kelvin. So if we substitute du and Cv, we will get dt, that is 21525 divided by 717.5 this Kelvin. So this will come something around 30 Kelvin. So this is the change in temperature. So the corresponding change in temperature of the air is 30 Kelvin. So these were all the questions from gas dynamics and propulsion. We have seen the solution, discussed the solution. So that's all. Thank you.